Hello, this is a video on electric field calculations following Young and Freedman's University Physics. Now, we've been talking in this chapter about electric fields. And in this section, we want to talk about what if I want to know the electric field at this point, right here. What is that, the electric field there? And the answer is basically that it is, we take vector addition and we add up all of the electric fields in the area. Now, I don't know if there are many, I don't think there are any strong electric fields in the area. I'm not feeling any tingling in my bones or my hair's not standing up. But let's say that we had some charges, in the vicinity that were creating electric fields. If I want to know what the electric field is at this point, I would have to do the vector sum of all the electric fields around. Now we know from earlier in this chapter on electric fields and such that the total electric force at a particular point is basically the vector sum or the superposition, call this the superposition principle, the superposition of all of the electric forces at this particular point. So the total force on this point right here is force 1 coming from this direction, electric force 2 coming from this direction, electric force 3, and so forth and so forth. Now, in this section, we want to extend that principle to the principle of superposition of electric fields. Now, remember, an electric field is basically a force per charge. So if we took the total number of electric forces at this point and divided it by all the, again, vector sums of all of the charges, pointing to this point, that would give us the electric field at this particular point. And the electric field at this particular point is going to be all of the teeny little electric fields added together. Now, charge can be distributed. And this particular section is a lot of examples. There's very little theory, just a teeny bit of theory. And then we have a number of examples that kind of show you how to play it out. And what the complicating factor is that charge can be distributed. So let's say instead of points causing all this problem, let's say that we have, say, a line. You've heard of a line dance. This is an electron line, da, 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 so you might have a charge distribution along a particular line. And we call the linear charge density lambda, which is charge in kind of one dimension. But you can also have a surface charge density symbolized by sigma, that is two-dimensional distribution. And you can even have three-dimensional volume charge density, that's a Greek letter rho, which is a three-dimensional distribution. Well, there are a number of examples in this section, so I've decided to do, I think, 3 videos to cover this section. I'll work through one that has a line charge density, and I'll work through one that has a surface charge density. But before we do those, the first example is very boring. Let's say you have 2 charges. Let's call this Q1 and this Q2. And let's say that they're both 12 nanocoulombs. Nano is 10 no, sorry, that's Mork and Mindy years ago. You don't know that, you're young. 12 nanocoulombs. Let's say one is positive and one is, that's 10 to the negative 9th. One is positive and one is negative. Now, positive, the way we conceptualize positive charges is that they are electric charge that goes away from it. So in every direction, we have an electric field that goes out from the positive charge. And then for a negative charge, we're thinking of the line's electric field coming toward it. So it comes in. So if we want to know, okay, what is the electric field at this point right here? That's 0.13 centimeters. I'm sorry, I didn't put centimeters there. I'm a bad person. But let's say a 0.3 centimeters away. And this is an isosceles triangle. So let's say that these angles are exactly the same. We have symmetry here. And so if we want to know what is the electric field at that point, how would we do that? Let's say that these are 0.1 meters apart or 10 centimeters apart. What is the electric field at point C, which is right here? By the way, this is called a dipole. When you have a positive and a negative, that's a dipole. All right, more on dipoles in the rest of the chapter. So let's figure out this puppy. So what is the magnitude? The magnitude is going to be the same because it's, well, it's 12 nanocoulombs in terms of the magnitude right here. But what is the magnitude going to be going from this to that particular point? Well, we have the formula, right? Well, we know that the magnitude is going to be the same. And so 1 over, what is it, 4 pi epsilon 0, that's 9 times 10 to the 9th, Newton meters squared per coulomb squared, right? That's a constant. And then I should probably have written out the formula, but it's in previous videos. And then then we have over Q, which for the field formula, and Q is, as we said, 12 nanocoulombs, 12 times 10 to the negative 9th. I went ahead and put 1.2 times 10 to the negative 8. Let's call the whole thing off. It means the same thing. And then the distance away is 0.13. And so 0.13 meters. And then it's r squared, right? The formula is 1 over 4 pi epsilon 0 times q over r squared is what it is. Just to make sure I'm not crazy. No, I'm not crazy. Okay, so that's the formula. We do all our math and blah, blah, blah. It comes out 6.39 times 10 to the third Newton per coulomb. Okay, so now we know what the magnitude of the force is. So both of these here, the force of this on that point and the force of this on this point is what we just said, 6.39 times 10 to the third power. All right, now, as I said, the positive point charge to the, well, let me do it mirror for you. The positive point charge points to the right, and the negative charge is pulling to the right. Let's go to this diagram. So the positive charge is pushing out, and the negative charge is pulling in. So both of these are going to combine in the same direction, namely the positive x direction, if we want to create a kind of Cartesian framework around it. And so we're going to have twice of something on that particular point. Now, what's interesting is the y forces are going to cancel out. Why? Because why? Because the positive is going up, right? The positive is going away from, and the negative is going down because it's pulling toward. And so whatever the y components would have been, we don't have to worry about them. They cancel each other out. So goodbye, y. But the x components are going to double, as we said. They're going to double because they're both pointing this way, I think, from your mirror image of what I'm doing. So we're going to have double, and then this is the amount. And then what is 5/13? Well, this is the cosine. The cosine, remember, is the adjacent over the hypotenuse. So since this is since this is 10 centimeters, half of that is 5 centimeters. So to get halfway here, we've got 5 is the adjacent side and 13 is the hypotenuse. So 5/13. We don't have to go ahead and we don't even have to use a calculator. Oh, I'm really disappointed. So 5 divided by 13 is the cosine of that angle, which is going to tell us what the x component is. And the x component comes out as 4.9 times 10 to the third Newton per coulomb. And then the I here says it's in the x direction, positive x direction. And so there's our example. So that is, there are, of course, a number of other angles on this situation. He takes a whole page and a half to do this problem in the book. I've done just a small sliver of it to give you a small taste of how you might find what the electric field is at a particular point right there, which is, there's no charge there in this example, based upon a dipole. All right, well, 2 more examples and we'll be done with this section.